Good afternoon, everyone. Thanks for the HKIs and my supervisor gave me this opportunity to share one of my work, BAI Zhaowen. And today I'm going to give a presentation about the thermal responsive hydrogel that applied in the aqueous lithium-ion battery for the self-protection. And this is the outline, so let's start with the background. And we know that energy is one of the most important problems for the humanity, and especially in nowadays. And we can see from here that the energy consumption increased several times since last century. And another thing is that at the very beginning, all the energy consumption was from the combustion of fossil fuel, but with the time going on, people find that we should try to use the more sustainable and clean energy resources. So the renewable energy resources start to participate in a very important role in the energy consumption. For example, the solar energy and the wind energy. And one issue is that for this kind of renewable energy, they always choose the electric as the final form. So this will cause one issue. That for example, the solar energy, they always convert the solar energy during the daytime, and the major consumption time is at night. So there is a big mismatch between the supply and the demand. So we need to build up a system to buffer this mismatch. And this system, we call it an energy storage system. And here are some different kinds of energy storage system. And among all these kind of systems, that the electrochemical energy storage system that has a good energy density and the capability to apply it in many areas. And among the different energy storage systems, that lithium-ion battery has a high gravimetric and volumetric energy density, so it attracts a lot of interest. And for the typical lithium-ion battery, that it contains one cathode and one anode. They separated by the separator to prevent from the short circuit. And the electrolyte here provides the ion migration medium. So during the charge process, the lithium-ion extract from the cathode and insert into the anode. And during the discharge process, the process is reversed, and we can see the current generated in the external structure. So by using different kind of electrolytes, the lithium-ion battery could be divided by different kinds. For example, the organic electrolyte which is most widely used, and for the solid electrolyte, people think this is for the next generation battery. And also the ionic liquid electrolytes that some people are working on it. So the interesting one is the aqueous electrolyte. It is because that the first battery in the world was using the water as an electrolyte. But after that, people find that the water will cause some serious issues, such as the water splitting, the electron dissolved in the water, and also the very narrow voltage working window. So it stops a while, but the aqueous battery also has some advantage, such as the low cost of the electrolyte, and both the electrolyte and the manufacturing during the manufacturing process, and it's environmental friendly. And even we mishand the aqueous battery, it will not flame and has very low possibility to be exploded. And the most important thing, the aqueous battery could be used as the fast charging and discharging and provide very high power density. So because of this kind of advantage, it attracts a lot of attention since last decade. And for this one, the fast charging it not only the advantage, but also will cause some problem. For example, during the fast charging, some heat will be generated and accelerate the water splitting and change the pH value of the electrolyte, and as a final result, cause capacity failure. So, in order to solve this issue, people try to use some method. Instead of add the thermal sensor in the battery and control the battery by the battery management system, people try to put something that between the electrode, so it could be worked at the room temperature, and when it is at high temperature, the battery will stop working. And the most important thing, this process should be reversible. And this one hydrogel was used for, first it was applied for the supercapacitor. You can see from here, when the temperature increased, that the electrolyte will the hydrogel shrink and squeeze the electrolyte out from the separator, so the LED light is off. And for this, by using this kind of strategy, people tried to different the method could be formed by different ways. For example, this people use is the hydrogel to form as a thin film, as a separator for the supercapacitance. And for this work, that people add the thermosensitive hydrogel that's polymer that's into the electrolyte. So when the temperature increase, the inner resistance increase, so the capacity decay. But when we see these two works, that we find that no matter you form a thin film or you add the thermosensitive polymer in the electrolyte, the reaction was not fully stopped. You can see there's still some capacitance and specific capacity here, which means that the reaction is there, the water splitting is there, so the issue is still there. So how could we, so back to our design, how could we want to do this? So we want to get porous hydrogel that could let the ion migrate, transport through that at room temperature, but carefully control the thickness, which also could provide a decent electrical performance. And after heating, the channel of the ions migrate will be blocked, and most important, it should be reversed. So how we achieve this? That we choose the AN and the NIPON, that the polymerized by the cross-linkage and MBAA. And we try to control the amount of the AN, so we can control the lower critical solution temperature. Because actually we want its use in the room temperature, and we do not want it stop working at a temperature which is not high. And here we also choose we carefully choose the substrate to control the thickness. And the most important thing for this hydrogel application is that we should choose appropriate lithium salt, because you can see from this figure, even the very low concentration lithium sulfate, that the water will drain out by the electrolyte, and for this one, it will stop working. The resistance, if we use this electrolyte, the inner resistance will be huge, even at room temperature. So after we tried several lithium salts, we found that the hydrogel has the highest tolerance for the lithium nitrate. And we also test the LCST temperature by different concentrations. Then we finally use 1 molar lithium nitrate as the electrolyte. And this is some characterization that we can see that at room temperature, the the hydrogel is hydrophilic, and when it's hit, when the temperature is hitting above the LCST, it's come to the hydrophobic, and this is reversible. And you can see the resistance here. Here is a SEM. This is the room temperature. We heat it to the LCST point, and take the SEM. You can see that all the channels block, and then we reduce the temperature. For sometimes it is reversible. So for the battery that we use LMO and LTP as cathode and anode, because LMO has three-dimensional lithium diffusion path, and the LTP has a Neskin structure, which is suitable for the fast charge and discharge. And the most important thing is that the voltage working window is suitable for this. The electrolyte is suitable for this system. And we can see that from the charge discharge curve and the cyclic performance, that we know that there's no much difference when they test it in the room temperature. And when we try the variation of the operating temperature, we find that the polarization of the battery decrease. It is because that at high temperature that the ion diffusion resistance will be smaller. But when the temperature increases to 70 degrees Celsius, we find that with the normal separator, it is still same. But for the one with thermal responsive separator, there's no current generated, which means that this self-protection works. And this is a EIS that would indicating that the resistance increased significantly after the temperature increased to 70 degrees. And the most important thing, this change is reversible. We can try it many times, and the battery still works. And this is a self-protection test, because that we know that the battery could stop working at the high temperature, but we don't know how the performance of the self-protection. So we try to operate the battery at 70 degrees for 5 minutes, and we find that there's nothing changed for the one with thermal responsive separator, but for the normal one, it has very serious hydrolysis at high temperature. And reflecting, and then we cool down the battery to room temperature, we find that the capacity decay by using the normal one, the separator is very fast than the thermal responsive separator, which prove that this protection is work. And at last is some demonstration about the LED, that we linked the battery with the LED light, and at room temperature, the bulb is on. And when we put it on the hot plate, it's shut off immediately. And then we put it down, it comes back again. And this work is still during the vision process. And that's all. Thank you.